Hey, so welcome to the second live stream, or rather, the second study session for the chapter 2 of System Design Interview book. Now, here, what we will be trying to do is we have already gone over scale from zero to millions of users in the previous live stream, and there we went over things like what is a single server setup looks like, what is a database, and SQL versus NoSQL, what are your trade-offs, then how do you go towards DB replication, why is it important, how to have a master-slave relationship, and then the use of cache, how CDN helps you be more available or reduce the time it takes to load your assets. Specifically for the context of this book, we have focused on static resources like your CSS, JavaScript, and other files. Then we went on towards what does it mean to have a stateless system versus a stateful system, and what is the idea behind why stateless systems are preferred and why it is not ideal to have stateful systems, and how it becomes sort of a blocker when you try to horizontal scale things. And post that, we went on how it is paramount and it is very essential to have multiple data centers, your application deployed on multiple data centers, so that in scenario of a disaster, business continuity is ensured. So disaster recovery plans sort of include the idea where if one data center is affected by some natural calamity, then all of your traffic is routed to some other geographically separate data centers. Then we spoke about message queues, how a publisher data is there, what's a consumer, how even when consumer is down, publisher can send the data and it can get processed. We talked about the payment service accepting the payment from the user, pushing the message of payment successful to a queue, then checkout receiving it, and if the checkout is down, then how it can consume messages from the queue later whenever it comes up. So that's about messaging queue. Then we briefly went over logging metrics, automation, what are their usages, how in the modern microservice mesh infrastructure, why it becomes so important. So we went over that. Then we spoke about DB scaling, how vertical scaling is not really ideal, and how it is sort of there is no scaling down of sorts when if you commit to a vertical scaling, because you are actually buying the resources or putting in, and it only becomes bigger compared to a horizontal scaling. What is a hashing function, and how does sharding works, and how do you ensure that the column or values that you pick when selecting a hashing function for your sharding should be that uniformly divides the database into almost equal parts. Then we spoke about celebrity problem, that even if we have shards on our database, but say when a popular celebrity posts something or when they do a live stream or whatever, the database shard that is holding their data specifically, it gets overwhelmed and it can cause apps to really slow down. A good example of this is Instagram slowing down when Messi won the World Cup. So you might have to give the celebrity a dedicated shard of their own. So those were the things we spoke out. And other than that, we also went over briefly how DNS works and what is the idea behind load balancers, and how do you cache, what is a gateway like, how to not have single points of failure, what is the importance of having multi-regional availability. So yeah, that was all about chapter 1, scale from 0 to millions of users. Now in this stream or video, we will be going over back of the envelope estimation. That is chapter 2 of this book. Okay, so yeah, that was a quick recap, and let's get started. So chapter 2, back of the envelope estimation. Okay, in the system design interview, sometimes you are asked to estimate system capacity or performance requirements using a back of the envelope estimation. According to Jeff Dean, who's a Google senior fellow, Back of the envelope calculations are estimates you create using a combination of thought experiments and common performance numbers to get a good feel for which design will meet your requirements. Okay, so you need to have a good sense of scalability basics to effectively carry out back of the envelope estimations. Okay, so far so good. The following concepts should be well understood: power of two, latency numbers, every programmer should know, and availability numbers. All right, moving on, let's see what are those. So, power of two. Although data volume can become enormous when dealing with distributed systems, calculation all boils down to the basics. To obtain correct calculations, it is critical to know the data volume unit using the power of 2. A byte is a sequence of 8 bits. An ASCII character uses 1 byte of memory. Below is a table explaining the data volume unit. Power to the 10. Approximate value 1000. Full name 1 kilobyte. Short name 1 KB. 2 to the power 20. That means 1 million. That is a 1 megabyte. Similarly, power 30 means 1 billion. That is 1 gigabyte. And 40 means 1 trillion. That is 1 terabyte. And 50 means quadrillion. That is 1 petabyte. So, latency numbers. Every programmer should know. Dr. Dean from Google reveals the length of typical computer operations in 2010. Some numbers are outdated as computers become faster and more powerful. However, those numbers should still be able to give us an idea of the fastness and slowness of different computer operations. Okay, L1 cache reference. If something is in L1 of your CPU, then 0.5 nanosecond. Branch mispredict 5 nanosecond. L2 cache reference 7 nanosecond. Mutex lock unlock 100 nanoseconds. Main memory reference 100 nanoseconds. Okay, 10 to power minus 9. Okay. Compress 1k bytes with Zippy 10,000 nanoseconds, that is 10 microseconds. Send 2k bytes over 1 Gbps network, 20 microseconds. Alright. Read 1 MB sequentially from memory to 50 microseconds. Round trip within the same data center, 500 microseconds. Disk seek 10 ms. Read 1 MB sequentially from the network, that is 10 milliseconds or 10 million nanoseconds. Read 1 MB sequentially from disk, 30 milliseconds. Okay. And send packet from California to Netherlands to California, 150 milliseconds. Okay. So let's just go in a bit more depth here. What exactly is the operation here? How it happens, and what even is, say, a mutex lock unlock, or what is a round trip meaning here. So yeah, let's go into the depth of these. Okay, so let's see how is this shaping up to be. So L1 cache reference. All right, so here we have loaded up all the latency numbers, and I have asked it to give me a more breakdown on what it is and how it works, and especially what we are trying to do here is this is a in speed hierarchy. So what is fastest, that operation comes at the top, and what is like the slowest and what happens in that is coming at the bottom. So yeah, that's how it is. Yeah. So these are the operations, and the fastest is the topmost thing, and the slowest will come at the end. So let's just go through it. So the speed hierarchy. Okay, fastest to slowest. L1 cache reference. What is it? L1 cache is the smallest, fastest memory sitting directly on your CPU chip. Okay. What happens when your CPU needs data? It first checks L1 cache. If the data is there, then there's a cache hit. Remember it similarly how we went over the cache, how it works, and how the cache hit or cache miss can happen. And there are eviction policies that you need to maintain, recently used FIFO and other things. Sort of similar, but at a CPU level. So this is the fastest cache that there can be. And this is essentially accessing memory that's part of the CPU itself. All right. So analogy, like reaching into a shirt pocket for your phone, almost instant access. So that's what this is. Why it matters. This is your fastest possible data access. Modern CPUs are optimized for cache locality. All right. Branch misprediction takes 5 nanoseconds. What it is? CPUs try to predict which way an if statement will go to pipeline instructions ahead of time. So when a code is converted via compiler into machine code and it is being run into your architecture, then it might have if statements. Then the if statements are converted into, say, an assembly equivalent or whatever ARM processor or whatever x86 processor that you are having. So basis that it tries to predict in what direction your condition might will go, if true or if not true. That is the scenario here. So if there is a branch misprediction, then it takes 5 nanoseconds for that. If the CPU guessed wrong, it has to throw away the work and it restart. And that costs around 5 nanoseconds. Why it matters? This is why sorting arrays before searching can be faster and why predictable code patterns at a CPU at a chip level they perform better. So when you say why my binary search is faster than searching for an element on a randomized array, this is what it is happening. At a system level, it knows that I have to discard the other half and I have to look into the other half, and it is a very predictable pattern rather than going if it is this, if it is this, and checking for all of the items. And that's essentially the efficiency that comes between O of log n and O of n. All right. So L2 cache reference, what it is. L2 cache is a level 2 cache larger than L1. L1 cache is usually 256 KB, but slightly slower still on the CPU chip. I will try to see now if I can load it up. Just a second. I will try to show my particular CPU's cache if I have access to it. Just give me a second. Yeah, so cache L1 data level 2. Yeah, perfect. I think this would help get my point across. Let me share this. CPU Z. Yeah, if you see here, uh, let me just move myself out of the way first. Yeah, perfect. All right. So if you see the L1 cache that there is 8 into 48 kilobytes, it is a 12-way data and instructions are there. Then level 2 cache if you see that is 8 into 1 megabytes. And then level 3 cache that is there on my CPU that is 8 into 1 megabytes. Sorry, level 3 is 96 MB. So this is what cache is and this is what the point I was trying to mean when I said that L1 cache is the smallest and then comes your, yeah, this is what I was trying to say, L1 cache is the smallest and then comes your L2 cache which is slightly larger and so on. All right, so yeah, I think that is what L2 cache reference particularly in this case means. So if data isn't L1, then we check if it is there in the L2 cache, and still it is fast, but it is not as fast as L1 cache. L1 cache takes like zero point 0.5, half of a nanosecond. So yeah, it's like checking. So what is branch misprediction? From a analogy of checking for your phone, branch misprediction is you putting your hand into your left pocket and realizing your phone is not there, and then taking the hand out and looking into other one. That is your branch misprediction. And L2 cache reference, it is checking your shirt pocket, but it is not there. Then you come and check and you reach into your jeans or your trousers, pants and check if the phone is there or not. That is your L2 cache reference. Not as fast as checking into your shirt pocket, but still very much faster because data is super close to you. So yeah, still incredibly fast. Okay, moving on. Mutex lock and unlock, what it is. A synchronization mechanism to protect shared resources in multi-threaded code. Now, what might happen is Yeah, so there is an analogy. Okay, so I'll go over that only. So there is a synchronized lock acquiring mutex. Then we do critical section, whatever the logic we want to execute on our code. And then we release the mutex safely so that other resources can use it. The thread must coordinate with the operating system to ensure exclusive access. Okay, why it matters. This is 200 times slower than L1 cache. This is why excessive locking kills performance. In high performance systems, lock-free data structures or careful lock design is crucial. Because if you take a lock for a larger time, then it becomes a bottleneck because then other resources can't acquire lock on that particular process. So main memory reference 100 nanoseconds. Okay. What it is, reading from RAM, not cache. What happens? Data travels from RAM sticks on your motherboard through the memory bus to the CPU, a much longer physical distance than cache, which is located on the CPU. Analogy. It's like walking to your desk drawer instead of your pocket. Why it matters? This is why cache friendly algorithms matter. Sequential memory access is much faster than random access because of prefetching that CPU is able to do. Now, number 6, compress 1 KB with Zippy. That takes 10 microseconds or 10,000 nanoseconds, what it is. Snappy Zippy is Google's fast compression algorithm. This is also used in Kafka and other places to compress the streams of your data. So what happens? CPU intensive operation that compress 1 KB of data. Why it matters? All right. So 100 times slower than RAM access. This is why you see compression used for network transfers. So yeah, that's what I was telling. So in Kafka, when you have a lot of messages, say imagine there are there's a medical device at a patient's home and it sends 5 messages per second and there are 1 million such devices. So, and what happens is these machines might be sending metrics if the machine is online. These might be sending AQI or some other two, three different parameters about the machine or the health of a particular individual that it is monitoring. Imagine it's a tele health system. Now, what would happen is now the streams of data, there might be different consumers for this data. There might be a person, say a nurse who is monitoring for the health. There is a service technician who is monitoring these events for ensuring that their service team identifies which machine has been down for too long and if they need to go and contact the person and if they need to service and make sure that this machine comes up online, and there might be a finance who is tracking how many machines are deployed, how much data we are receiving, and things like that. So 5 messages per second, and then a machine is sending them through the network. And what happens is there are 1 million such machines deployed. So there is almost like 5 million messages per second. That is a big stream of data coming in. Now, what happens is if you are using Kafka for this, then sending this much of a traffic over the internet, you need to compress and decompress, like serialization, deserialization from the sender and receiver, agreeing on a specific algorithm. So that's where this algorithm comes in. Snappy, Zippy, these are the algorithms by Google. So CPU intensive operation that compresses 1 KB of data. That's what happens. And that is also a parameter on which these compression algorithms are determined or judged on, is what is the type of compression you want to do. Is it does that you want to just compress it faster, or is it that you want to save up on your space bandwidth? So what is your constraint? Are you more worried about not racking up your bandwidth internet cost, or are you more worried about your CPU utilization? So that's why LZF, Snappy, ZP, these are various algorithms which are there and which are used for fast compression. So why it matters? Because this process is 100 times slower than RAM access. This is why you see compression used for network transfers reduce the bytes that are being sent and disk storage to reduce the space. Okay, but not for in-memory caching. Compression overhead isn't worth it for RAM. All right. Then we come to sending 2 kilobytes over 1 Gbps network. What it is, sending a small packet over a fast network. What happens? Application writes to socket buffer. OS kernel processes the data. Network card transmits that packet which contains the data. Data travels through switches, routers. Why it matters? This is 200 times slower than RAM. This is the foundation of why microservices have overhead. Every call equal to network trip. You need to call some other microservice, you need to get the data, or you need to handle if they do not send the data, and things like that. Why batching requests matter. Why you should cache aggressively and why you should cache on the data that you know isn't going to change that often. So that is sending 2 kilobytes over 1 Gbps network. Now reading 1 MB sequentially from memory. Now this takes 250 microseconds, what it is. Reading a larger chunk from RAM sequentially. Alright. What happens? Modern CPUs prefetch data efficiently. That is, reading 1 MB equals to 1000 kilobytes, but not 1000 times slower than 1 KB because of batching or prefetching. Okay. Why it matters? Sequential access patterns are much faster than random access. Yeah, we went over it already. So round trip within the same data center takes zero point 0.5 milliseconds or 500 microseconds, what it is. Network round trip to another server in your data center. What happens? Your service goes through the network switch, calls another service, whatever is needed, then comes back. Then this includes network latency, OS overhead, and processing time of the request on the another server to provide you with whatever it is that you are looking for. For example, there is a service A which handles all of your authentication. Then there is service B which stores user profile. Okay, I think this is trimmed down here. Uh, so much hype about Gen AI and AGI, but Claude can't manage the context in which it is working. But anyways, so yeah, the example I think here what it was trying to say is कि when service A has the auth and when it determines that auth is successful, it calls service B. Now service B might have its own containers that are deployed on a cluster. What will happen is the request goes to a load balancer, it gets redirected to a server basis the load balancer policy, then the user profile details are fetched that needs to be rendered, then that API or resource is called, and then it is sent back over the network. So this whole thing round trip within the same data center, assuming within the same geographical availability zone, both of these are, it's just that they are in different containers, then this would take around zero point 0.5 milliseconds. Alright, so why it matters? This is 5000 times slower than RAM. Microservice architectures need careful design solely due to this. You need to optimize how you are calling. When you are calling, there should be a sufficient cache layers in between. Service meshes add latency. Each hop adds zero point 0.5 milliseconds between different services. So if you have an even more complex system, say you determine if the user is allowed to do the payment or not, then you call checkout and then you ask what are the instruments that needs to be shown. Especially when you call checkout, checkout itself calls another microservice that stores all of the payment instruments of a particular user. They come back, and then when instruments are fetched, then these are populated on the app, and then you call the payment service. Payment service then itself calls the payment provider. So if you see, there are 4 or 5 hops in between here, right? So each bit is adding latency approximately worth zero point 0.5 milliseconds. So that's what these are. Then Netflix, Uber use circuit breakers to handle this. Now the idea, I'll go over it briefly for now. Basically, the idea behind circuit breakers is that when a particular, so a circuit is closed, then data keeps flowing. But when say there is a latency or there is a condition on which we break a circuit, the circuit becomes open. The circuit becomes open when there is high latency or there is a more than the time that we have defined for a particular network or resource call. When it exceeds, then a circuit breaker open, and usually what happens is you would log these instances and you would create your real-time Grafana or PagerDuty alerts based that, so that on-call engineer is informed that hey, this was your service, and on this bit this circuit is open and data is not flowing. So this is what circuit breakers are used between inter-service hops and how it is handled. Now moving to disk seek, what it is. It is so you have a disk, hard disk, and you have a platter head, which goes on and fetches the data from different locations, right? So moving the read or write head on a spinning hard drive to the right location, this takes 10 milliseconds, and physical mechanical movement is what it is happening here. The disk platter spins and the arm moves to position. Why it matters? This is 100,000 times slower than RAM, and especially because of this, when you understand this nuance, you see that solid state drives, SSDs, are revolutionary. They have no seek time, and databases use sequential writes or append only logs. Random disk access kills performance. Okay, so reading 1 MB from network. All right, so when we try to read 1 MB over the network, inter-service or internet, what happens? Multiple packet round trips, then TCP congestion control, potential retransmissions in between. So that is what is happening here. So now why it matters. Same as a disk seek. This is why. CDNs cache content close to users geographically, what we learned in the last chapter as well. So we paginate API responses, and chunked uploads or downloads exist due to this. Because it takes 10 milliseconds, which is a lot of time compared to accessing the data locally or say from cache from where we started. So now reading 1 MB from disk, this takes 30 milliseconds. Reading 1 MB from HDD spinning disk. All right. Reading 1 MB from HDD, what happens? Seek plus read time. So this is seek, that is 10 ms, plus read time. Disk must physically rotate to read all sectors. Why it matters? 3 times slower than network. Network takes like 10 ms. Reading 1 MB from disk takes 30 ms. SSDs change everything. They are 100 times faster. And databases heavily use caching. Disk is the new tape. Basically, what they mean by in the old times, there used to be tapes, and of course, like it's old time for me also. Disk is the new tape. You used to write on the tape, and then you would have devices that would read from them, and it was a cumbersome process. So, disk writing any data to the disk is the new tape, and it takes more time than it takes to read from the network. So, might as well have your resources on the network and you do the fetching from there. So that is the idea behind this. All right. So send packet. Okay. So they are sending packet from California to Netherlands and to California back again. This takes 150 milliseconds. What it is? This is intercontinental round trip time. We went over the round trip time in a single server, that is 500 microseconds. But now what this is intercontinental round trip. Packets travel more than 20,000 kilometers through undersea cables, multiple routers across continents. Why it matters? This is 1500,000 times slower than RAM. You can't fix because why they say speed of light is because they are using optical fiber cable here. So that is not something that is like a universal constant. So you can't fix speed of light. Regional deployments matter, and that's why you should not be doing California to Netherlands and then back to California with the response or whatever. Rather, you should have a data center which has geographical condition, load balancer, where you geo redirect users based on the location from which the traffic is coming and having your own deployment for that particular environment. So, yeah, you should have that. Regional deployments matter. That's what the second point means. And WebSocket connections make sense for chat apps. Okay. GraphQL batching reduces round trips. More on WebSocket and GraphQL later on. But yeah, that was a comparison from as local or as near proximity L1 cache fetch to the another continent fetch, which takes like 150 milliseconds. All right. So what we understand from this is ideally that Locality matters, especially keeping hot data in cache, and that's the reason why there's a lot of emphasis on data structures, how you are using, are your data structures read optimized, are your data structures sorted, and how the fetch or seek is happening. Because sequential is always greater than random access. Network is expensive. Batch operations read 100 items versus 100 individual reads. That's why you should batch your request. And there's something similar what Kafka also does. It has a local buffer. All of the message that needs to be sent, it keeps collecting them. And when that buffer size is reached, then it sends out those messages in batches so that network write or read is optimized. Cache aggressively. Redis memcached by Facebook. These are the ones that are used a lot. Then using CDNs for static content. Yeah, we have a lot of these things in the first chapter. So disk is slow. Disk is the new tape, as it said. SSDs are 100 times faster than them. Databases use write ahead logs, sequential writes. OS page can help. OS page cache helps tremendously. Okay, more on this later. Lock kill performance. Use lock-free algorithms when possible. We went over mutex and which ones to why when a resource is in a lock, then it sort of becomes a bottleneck if it is not released properly. And keep critical sections tiny. Consider async or event-driven patterns, messaging queues, things like that. Geography is physics. Multi-regional deployments reduce latency. Like simple. Uh, Data is traveling at the speed of light through optic fiber cable, but if you reduce the length of that optical fiber cable by having less distance between your users and data center from which data is coming, then you are reducing the size of the optical fiber cable in some sense. And if you can't change the speed of light, you can reduce the distance that it has to travel, right? So that's what this means, key physics, right? Edge computing helps. Okay, edge computing is another, not a recent trend, but yeah, doing things on the user devices as much as possible. But like, take it with a pinch of salt. It has its own nuances and designing it. So yeah, that was about the various network calls and how the data is fetched from various places. So a small example why caching works. Okay, just for example, we want to do a user profile lookup without cache. Database read from disk, 30 millisecond into 1000 requests per second. We can't handle it. That is a lot because that will be like 30 into 1000 requests at 30,000. That's like a lot of time. 30 seconds it would take to handle those, which is not ideal. Essentially, there is some data that if a request takes more than 10 seconds or something, 90% of the users drop and they never return, something like that. So yeah, we wouldn't want to do that. So now with cache, Redis in memory, zero point 0.5 millisecond data center round trip into 1000 requests per second, which is like way faster. All right. So now going on to with local cache that is in process, which is way more faster. So that is what the comparison is. This is why Netflix use L1 in process cache, JVM heap, then L2 Redis memcached shared database, and then L3 is where they have database. If both of these cache fail, okay, then they hit the database. All right. So that was about how the different latency numbers that every programmer should know. Now I'll switch back to the book. Okay, looks good. Okay, moving on. INS nanosecond, microsecond, millisecond, -9. Then yeah, all of the pretty known numbers. Okay, a Google software engineer built a tool to visualize Dr. Dean's numbers. The tool also takes the time factor into consideration. Figure below shows the visualized latency numbers as of 2020. This is what 1 nanosecond is, one black block. L1 cache reference is 1 nanosecond. Branch mispredict is 3 nanoseconds. Earlier, as per 2010, it was 5 nanoseconds, I think. Yeah. Now it has come down to 3 nanoseconds. Okay. And then L2 cache reference is 4 black blocks. All right. Mutex lock unlock, acquiring a lock on a resource is 17 nanoseconds. And this is what 100 nanosecond looks like, and this is one block. Okay, this is 1000 nanoseconds. Compress 1 KB with Zippy is like 2 microsecond. That is like two rows of these 10 blue, which is like 100 each, 1000 and 1000, 2000. All right. Now moving ahead. So what happens next is, yeah. So 10,000 nanoseconds is like 10 microseconds, which is one green dot. So if you take this one green dot would contain 10 of these, and each blue one would contain this. So imagine 10 of these would equal to one blue block. Oh, sorry, one row of blue blocks. Yeah. So send 2000 bytes over commodity network. That takes 44 nanoseconds. One blue is one green is 10 microseconds. Okay. Send 2000 bytes over commodity network, 44 nanoseconds. All right. And then SSD random speed is 16,000 nanoseconds or 16 microseconds. Okay. Read 1 million bytes sequentially 1 MB from memory. That's like 3 microseconds, which is this. All right. One 3/10 of this green block. Round trip in same data center 500. God, that's a lot. Okay. 100, 200, 300, 400, 500. Okay. Perfect. Yeah, let me get a pen. Yeah. 100, 200, 300, 400, 500. Okay. Now what happens is we go over 1 million nanosecond means 1 millisecond. All right. That we will denote with a red block. Now going to the red block, reading 1 MB from SSD takes 49 microseconds. Now 49 microseconds is there. Disk seek takes 2 ms, 2 ms, 2 milliseconds. So which is this? And packet round trip 150 milliseconds. So yeah, this is 15 of them, and that's what it takes to do a disk seek. All right. Moving on from this, let me get rid of it. Okay, yeah, looks good. Okay, so these were the conclusions from the Jeff Dean's research and as well as the recent data. Memory is fast, but disk is slow. Avoid disk seeks if possible. Simple compression algorithms are fast, like Snappy Zippy that we spoke about. Compress data before sending it over the internet if possible. Data centers are usually in different regions and it takes time to send data between them. Okay, now let's look at availability numbers. What is availability? What do we mean? We have a 99% of time or we need 99.9% of time and things like that. How does that translates into how much downtime you are allowed to have on your service in a day, in a year? So let's go over that. High availability is the ability of a system to be continuously operational for a desirably long period of time. High availability is measured as a percentage, with 100% means a service that has zero downtime. Perfect. Uh, Almost nothing with 100% uptime exists. But yeah, most services fall between 99 and 100%. Yeah, exactly. A service level agreement. SLA is commonly used term for service providers. Now, what is this whole terminology of service providers? For example, you are an org which is handling the complete infrastructure, hosting, app, and service providing to the government for their medical app, for say hospital booking or whatever. Then, because medical or hospital is a critical infrastructure, when you were getting the contract from the government, you would have also signed a contract which had some requirements that this is the service level agreement between you as a service provider and the government, the consumer in this case, that your app needs to be up or your app needs to be working at least this much time and you can't afford more than this point of downtime, more than this percentage of downtime. So that's what the service level agreement between provider, service provider, and customer, it means. And this agreement formally defines the level of uptime your service will deliver. Okay. So cloud providers, Amazon, Google, and Microsoft set their SLAs at 99.9% or above. Now, why talk about these? Essentially, because these are used as the benchmarks in the industry that whenever you provide a service or something, this is what they, hey, this is what the giants are doing. And these are the uptime that they have promised. And ideally, you can compare how critical and uh, not so critical your service is, and basis that it is, you can define your services uptime. So yeah, what does 99% availability means? Means a downtime of 14.40 minutes per day and 3.65 days, which is pretty simple because 1% of 365 days is 3.65 days. So that's how it is calculated. Now, how do you come at the number of 99.9%? So 100 minus 100, just a second. Let me share my entire screen. Yeah. So how would that work? Let me show. So 99% uptime, right? Let me get this. Yeah. So we have this, right? All right. So how would this work is 100 minus B7 into 365 days into this, what we will do, and in days, in hours. All right, let's see. So if we do this, then it becomes percent, right? Yeah. Okay. In hours, it becomes P7 into, okay. But for 99.9, it becomes 8.76. Then for 99.99%, it becomes 0.876 hours. In minutes, I'll also do. That's equals to, yeah, in minutes. Also, might as well do in seconds also. Yeah, so that is 99.99. 99.999 is 315.5.26 minutes, and 99.9999 is less than 31.56 seconds of downtime. If I am designing the, okay, let's just search which systems in computer science have 99.999% uptime. Systems that achieve are typically mission critical and safety critical systems engineered with extreme fault tolerance. 5 nines availability. All right, let's see that. Achieving this level of Achieving this level of availability translates to approximately 31 seconds of total downtime. Telecom systems, traditional telephone exchanges, and modern communication networks, specialized hardware, fault tolerant software platforms, build applications across multiple cloud, highly engineered architecture. Say, if I was building the microcontroller or sub network code that manages auto driving steering in a Tesla, then even 1 second can be a question between life and death. So that is when you need systems with that much of a high 6979s level of availability. And yeah, so that was a theoretical derivation of how much times it takes and availability. Okay, derived. Yeah, so we just derived it using the formula that 100 minus whatever is the uptime you want, and in days, hours, minutes, how would that breakdown look like? So yeah, uh, good enough. We were able to get the same numbers. So yeah, I think we understand this concept. Now moving on. Example, estimate Twitter, UPS, and storage requirements. Please note that following numbers are for this exercise only. They are not real numbers. So let's assume, how do you go on about estimating queries per second for Twitter and storage requirements? Now say Twitter has 300 million monthly MAUs. All right. Let me get my pen on here. Yeah. 300 million monthly active users. All right. Sounds like a fair number. Okay. Now 50% of users use Twitter daily. So that would become 150 million. Now user posts 2 tweets per day on average. So 150 used daily into 2 tweets equals to 300 million tweets. Okay. Yeah. 10% of tweets contain media. So 30 million contain media in them. Right? Looks good. Data is stored for 5 years. Okay. Daily active users 300 million into 50%, that is 150. QPS 2 tweet 24 hour per 30 second. So queries per second comes down to 3500 queries per second. Peak QPS, say it is IPL final or some World Cup, FIFA World Cup final, something like that. Then it might go to 7000 QPS. Now media storage. So we can assume that a tweet ID will be 64 bytes, text will be stored into 140 bytes, and media 1 MB. Media storage, that is 10% of every 2 tweets that users say across 150 million users. That is 30 whopping TB per day. Now 5 year media storage, that is like 55 petabytes of data. So yeah, that's how you would estimate for Twitter, and what is called having a taking a safe estimate versus just taking a vibe estimate. This is more of a good guesstimate approximation of this. So a few tips. Back of the envelope estimation is all about the process. Solving the problem is more important than obtaining results. Interviews may test your problem solving skills. Here are a few tips to follow. Rounding and approximation. It is difficult to perform complicated math operations during the interview. For example, what is the result of 9987 by 9.1? There is no need to spend time going over this. Just keep it as a number. You are not a calculator. You are someone who takes decisions, and those can be delegated. So you can just write and go on with this. There is no need to spend valuable time to solve complicated math problems. What I did here when I showed you how the approximate times and uptimes look like, this is not something that you need to say. You can just say 99.99% of time is what we are aiming for here, and you can move on with that. It is for my own understanding and competence that I wanted to derive that. Okay. So there is no need to spend valuable time, all right? Yeah. Precision is not expected. Use round numbers and approximation to your advantages. Convert that 9.3 to a 10 or a 9 and take the alignment of the interviewer before moving forward in this. The division question can be simplified as follows: 100,000 by 10. Write down your assumptions. It is a good idea to write down assumptions to be referenced later. Why write assumptions? Because when we started, and had we not made the 10% of tweets contain media, then we would have not been able to do this calculation how much storage it will take a day. So yeah, that's why write down your assumptions and label your units. That is very important, especially when there are multiple data component bits. How big of a user ID is looking like, how much will be the size of a tweet, how much media are we assuming is going to take, 5 KB, 5 MB. Just don't write 5 and move on, because then your interviewer might see that as a sloppy work, because you yourself will go around in circles figuring, or when your derivation say maybe goes wrong, that what was the unit of this particular thing. Commonly asked back of the envelope estimations: queries per second peak, queries per second storage, cache, number of servers, etc. You can practice these calculations when preparing for an interview. Now, again, practice makes perfect. Congrats on getting this far. Congrats to you as well for sticking with me throughout the study session. Now, yeah, that's the end of the chapter. These are some of the reference materials which were mentioned at various points during the chapter. The next chapter is going to be a framework for system design interviews. That is a topic for another stream. That's all for today. Thanks a lot for joining. And yeah, again, wanted to apologize. Last video, there was a bit of echo. At some point, I plan on redoing the whole video. But for now, I'll stick with going through this whole book first. And I hope, as I promised, the quality of this video is better and there is not that much of an echo, and quality wise this one is better, I feel. And yeah, anything especially good or bad, especially the bad, something that I can improve, something that you did not like, let me know in the comments. I'll try to incorporate those things. So yeah, thanks a lot for tuning in. That was chapter 2 of system design interview. This stream I will end now. I will also post it on my YouTube channel pretty soon. So yeah, you can watch that later on as well. I have created a course where I'll be uploading all of these chapters in there. Yeah, thanks a lot. Okay, bye.